Hello, and welcome to this introduction to the Gurobi Interactive Shell. My name is Ed Rothberg. I'm the Chief Operating Officer and co-founder of Gurobi Optimization, and I'll be your presenter. The intent of this video is to give you an overview of the Gurobi Interactive Shell. I should note that this isn't meant to be an introduction to mathematical modeling. I'll be assuming that you're already familiar with math programming and are already able to build linear and mixed integer programming models. I'll be talking about how you would work with such models from within the Gurobi Interactive Shell. The Gurobi Interactive Shell is really the face of the Gurobi Optimizer. It's what you see when you double-click on the Gurobi icon on a Windows machine, for example. Gurobi Shell is a tool that allows you to interact with the Gurobi Optimizer. The most common use is to do basic experimentation with an existing optimization model. You can use the Gurobi Shell to read a model from a file, solve it, examine the solution, modify parameters, modify the model, etc. The shell actually allows you to do a lot more though, so I'll be giving an overview of the sorts of things that are possible with the interactive shell. This video will have very few slides. I'll spend most of my time typing commands directly into the interactive shell. This will allow you to see how the shell is used, what the output looks like, and I actually recommend that you follow along at home. You can fire up the interactive shell and type in what I type in. I should warn you that I intend to go pretty fast. Since this is a video presentation though, you can always hit the pause button if you need time to catch up. Here's a brief outline of what I'll be presenting. As I mentioned, I'll start this video with an overview of some of the more common, more basic things you're likely to want to do from within the Gurobi Interactive Shell. For example, I'll show you how to read a model from a file, optimize the model, display the optimization results. I'll also show you how to modify optimization parameters if you want to experiment with the effects of different parameter settings on your model. For example, if you want to try using the interior point solver instead of the dual simplex method for solving a linear model. I'll also tell you how to get help from within the interactive shell. We include a pretty thorough help system that gives information on pretty much everything you're likely to want to do from within the interactive shell. Then I'll move on to a few more advanced topics. I'll show you how to perform some more sophisticated queries on the results of an optimization run, and I'll also show you how to modify your optimization model through the interactive shell. Then I'll show you how to customize the Gurobi shell. You'll see how to write your own custom functions that allow you to add your own custom commands into the Gurobi shell. I'll also show you how to write simple callbacks that allow you to modify the behavior of the Gurobi Optimizer. And finally, I'll show you how to use the Gurobi Interactive Shell to build optimization models from scratch. So let's get started with the basics. I'll assume that you've already installed the Gurobi Optimizer on your machine and that you're ready to launch the Gurobi shell. Now I should say that I'll be using a Windows machine for this video, but once the Gurobi shell's been launched, everything I do will apply to the Linux and Mac versions as well. On Windows you have a few options for launching the Gurobi shell. You can launch Gurobi from the Start menu by selecting the Interactive Shell option from the Gurobi folder. You can also double-click on the Gurobi icon that we install on your desktop. Let me demonstrate that now. This is the Gurobi icon on your desktop. Double-click on that. And this is the Gurobi shell window with the Gurobi prompt. I'll actually close this and show you the third option, which is to launch Gurobi from a Windows command window. So from a command window you just type Gurobi, and again that launches the Gurobi shell. If you're on a Linux or Mac system, you'd launch the Gurobi shell by just typing gurobi.sh into a terminal window. Now that we've launched the Gurobi shell, let's just dive right in and read an optimization model from a file. I've brought up file p0033.lp in a text editor. This file contains MIP model P0033 from the MIPLab set. This model is stored in LP file format, is a file format that is meant to be human readable. So as you can see, the file specifies a linear objective to be minimized. So 171 times variable C157 plus 171 times C158, etc. Below that, we have a set of linear constraints that must be satisfied by the solution to this problem. So, for example, in the first constraint, these four variables, the sum of these four variables, must be less than or equal 1. So we have a set of linear constraints on these variables. At the bottom of the file, we have a section which indicates that these variables must take value 0 or 1. These are binary variables. So this file specifies a mathematical programming problem to be solved. We actually include this file in the Gurobi distribution. It's in the examples/data directory. The Gurobi Optimizer can read models in either MPS or LP file format. LP is the format shown here. MPS is a common file format as well. It's much less human readable. So these are the two most widely used file formats for math programming models. How are we going to read this file? Well, the Gurobi Interactive Shell has a read command that takes the name of a file as input. So m equals read p0033.lp. So this read command takes the file name as input and it produces a model object as output. So we need to store that object into a variable. So what we've done here is we've taken the output of the read command and put it into the variable m. The read command indicates that it read an LP format model from file p0033.lp, indicates how long it took, and it provides some statistics about the model. The model contains 15 rows, 15 constraints, 33 columns, 33 variables, and the constraint matrix contains 98 non-zero values. So now we have an object, a model object. What can we do with this model object? Well, models have several methods that can be invoked on them. The first method I'll invoke is a method called printStats. So we say m.printStats. So what this did is it took the model stored in variable m and invoked the printStats method on that model. And this prints statistics about the model, gives the size of the model, 15 constraints, 33 variables, variable types, 33 integer variables, all of them binary. Gives some information about the coefficients. It shows you the minimum and maximum values of the coefficients in the constraint matrix. These are absolute values over all the non-zero coefficients in the matrix. So the minimum absolute value of any non-zero coefficient in the matrix is 1. The maximum is 400. Gives you the same information for the objective coefficients and for the right-hand side. The next method I'll invoke on the model object is optimize. This instructs the Gurobi Optimizer to compute an optimal solution to the model stored in the object. So m.optimize is a command I type. The model is stored in object m. So you can see the Gurobi MIP log here. Logging for continuous models is different. I'll actually show you that in a minute. So let me go quickly through the contents of the Gurobi MIP log. So the first step in optimizing a model is to perform a pre-solve step. Pre-solve attempts to reduce the size and the difficulty of solving the model. So in this case, pre-solve was able to remove 2 rows and 5 columns from the model, giving us a model with 13 rows, 28 columns, and 91 non-zeros. Next step in the MIP optimization process is to apply heuristics in order to find feasible solutions to the model. In this case, the heuristic found a solution with objective 3412. So this is a feasible solution. It's not necessarily an optimal solution. So the next step in the optimization process is to try to either prove that this solution is optimal or find the optimal solution. And this is done through branch and bound. And the progress of the branch and bound is shown in this section of the log. There's several fields here. There's quite a bit of information about the progress of the optimization. You can find documentation on the meaning of all these fields in the reference manual. I'm not going to go through that in detail here. I just want to point out that for this particular problem, we explore the root node. So actually we only explore node 0. This column here indicates which node we're exploring. The log indicates at all times an upper bound and a lower bound on the optimal objective for the model. So in this case, to begin with, the upper bound is 3412. This is the solution that was found by the heuristic. And the lower bound is, to begin with, is 2838.54674. So this is the solution to the root relaxation, the LP relaxation of the mixed integer programming model. And the current optimality gap is 16.8% at this point. So as I mentioned, on this model we spend some time exploring the root node, node 0. Each of the log lines here indicate that we've done one round of cutting planes. We've added cutting planes constraints to the model to try and tighten the relaxation. And each round of cutting planes increases the lower bound on the optimal objective. So before the cutting planes, the lower bound is 2838. After one round of cutting planes, it's 2928. 2 rounds, it's 2954, and so on. During the root node, in addition to applying cutting planes, we're also continuing to apply heuristics to try to find feasible solutions. In this line here, the H indicates that this line indicates a heuristic solution has been found. So the heuristics find a solution at 3347. And the heuristics find another solution at 3089. And it turns out that that this solution is optimal. It doesn't actually show the lower bound increasing up to the value of the upper bound, but once we found the solution of 3089, we're able to increase the lower bound to be equal 3089. Once the lower bound and the upper bound are equal, then we have an optimal solution. So at this point, we've solved this problem to optimality. The last part of the log gives a summary of the solution process. In this case, it shows we explored 0 nodes. So this problem was solved at the root node. 56 simplex iterations in total. Total runtime was 0.02 seconds. It says that the optimal solution was found to the tolerances. The default gap tolerance is 10 to the minus 4. And the best objective was 3089. The best lower bound was 3089, so they're equal. So the optimality gap, the difference between the lower and upper bound, was 0. So that was a fairly easy model to solve. Let me show you what the log looks like for a more difficult model. I will now read in model glass 4. This is another model from the MIPLab set. We've also included it in the Gurobi distribution in the examples data directory. So I've read the model in, and then I'll type m.optimize. And as you can see, we're not solving this model at the root. We processed the root node, added some cutting planes. In this case, the cutting planes did not actually improve the value of the relaxation. We're continuing to solve the problem. We found many solutions. H indicates the heuristics found a solution. The star indicates that a solution was found during the branch and bound process, just in the process of solving relaxations. At this point, we've explored almost 500,000, actually now more than 500,000 nodes in the branch and bound tree. The gap between the lower and the upper bound is still substantial. The gap is 26.7% at this point. I'm actually going to terminate the run right now. I can hit Control-C. It will interrupt the optimization. And you see that in the process of exploring this branch and bound tree, we explored almost 1 million nodes in 56 seconds. We interrupted the solve, and the best objective was 1.50000129. The best bound was 1.1000, And the gap at the point at which we stopped was 26.67%. So at this point we have not found an optimal solution to this problem. I mentioned that the log for a continuous model looks different from the MIP log. So let me show you the continuous log now. I'm going to read model pilot S. This is a model from the netlib set. We don't actually include this in a distribution, but it can be downloaded from the web. If you just do a search for netlib and pilot S, this is a well-known model. It's been around for probably 30 years. So I've read the model, and now I'm going to call optimize. I'm going to use the default solver, which is the dual simplex method for continuous models. And this is our log for continuous models. So again, for continuous models as well as integer models, we start with a pre-solve step. Try and reduce the size and difficulty of solving the problem. In this case, pre-solve removed 313 rows and 660 columns, leaving a model with these dimensions. This in the dual simplex log, this is followed by log lines that indicate the current simplex iteration, the objective value for the current basis, the current basic solution, and then the magnitude of the primal infeasibility and the dual infeasibility for the current solution. And in simplex, when the primal infeasibility and the dual infeasibility are both 0, you found the optimal solution. Finally, we have a summary section which indicates that we solved this problem in 3,658 dual simplex iterations. It took 1.48 seconds, and it indicates the optimal objective for this model. So once you've optimized the model, likely next step is to look at the solution. So this model here, this LP model, Pilot S, is a bit large and unwieldy for working with the solution on the screen. So I'm going to read a model we worked with earlier, P0033. I'm going to optimize this model. And now, so at this point we've seen two methods on the model object. We've seen print stats, which prints statistics about the model. And we've seen optimize, which computes the optimal solution for the model. Next method I'm going to show you is print attribute. So attributes are an important concept in the Gurobi Optimizer. I will return to this concept shortly. For now, let me just say that what we want to do here is print the X attribute. The X attribute is the solution, the currently loaded solution. And when I say m.print attribute of X, what I'm saying is for each variable where the current solution value is non-zero, print the value of that variable. And recall that model P0033, all the variables were binary. So all the variables must take value either 0 or 1. So these are the variables in the optimal solution that take value 1. Alright, so let me now look at a slightly larger problem. I will read model Bell 5. This is a MIP model from the MIPLib set, slightly larger than P0033. I will call optimize on this model. We found an optimal solution, and now I call m.print attribute of X. And well, basically it scrolls off the screen. So this is still a fairly modest sized model. This model has 104 variables, 104 columns. So imagine you're working with a model that has thousands or millions of columns. So how can you work with print attribute? One thing that we've included in the print attribute method is a filter. And so instead of saying print attribute of X, you can say m.print attribute of X, and then the second argument is a wildcard. Basically allows you to say print all the values of the attribute X for variables whose name match the filter. So you can see here that what we've got now is the list of all variables F star, variables whose names begin with F, and all variables whose names begin with F who have non-zero X values. So print attribute actually it's fairly flexible. It gives you a fairly complete reporting system. So print attribute can be used to show you the value of one attribute. It can actually be used to show you the values of a list of attributes. So for example, m.print attribute, oops. So there's a lower bound, an LB, a lower bound attribute, an X attribute, and there's also an upper bound attribute which gives the upper bound for each variable. And then let's use our same filter. So what this is showing here is it's showing us the lower bound, X, and upper bound attributes for all variables whose names begin with the letter F. And again, we filter based on variables that have non-zero values. In this case, it's showing us all the variables whose name begin with F because they all have non-zero upper bounds. So if any of the attributes that are requested have non-zero values, then the corresponding variable is printed by print attribute. So as you can see, print attribute is a pretty flexible method. It gives you a fair amount of power for doing solution reporting. So another thing you can do with the solution is you can write it to a file. Let me actually go back to P0033, which is a smaller model. Optimize this model. So we can use the write method on the model. And we can write P0033.sol. The .sol suffix indicates that we want to write the solution to a file. So at this point we've written the solution, the optimal solution to this model to a file. There's actually another capability in the interactive shell, the system command, that allows you to just issue shell commands. So DOS shell, in this case I'm using Windows. For Unix you can issue standard shell commands. So in this case I'm going to issue the DOS command type P0033.sol. And what you see, this is the contents of the file P0033.sol. So it's written the solution, the optimal solution to model P0033 to a file, and this is the contents of the file. So for each line you have the name of the variable and the solution value for that variable. So another thing you might want to do when using the interactive shell is to set Gurobi parameters. So you may want to use the shell to experiment with different ways of solving your model. So I will demonstrate the setParam method on the model object now. Let me load a more difficult model. This is class 4. This is the model that we were unable to solve in roughly 60 seconds before. And I'm going to use the setParam method to set the Gurobi heuristics parameter to value 0.5. So Gurobi has a extensive set of parameters you can set. They're documented in the reference manual. I'm not going to go through the full set of parameters here. I'm just going to talk about how you set them. In this case, the heuristics parameter, we've changed the value to 0.5. The previous value was 0.05. The minimum was 0. The maximum was 1. So this parameter tells the Gurobi Optimizer how aggressively to apply heuristics. 0 means don't apply them at all. 1.0 means basically spend all your energy on heuristics. 0.5 is, of course, as you can see, it's larger than the default. And now if we call optimize on model class 4, what you'll see is it's somewhat subtle, but you'll recall that when we tried solving class 4 with defaults earlier, we eventually found a solution of 1.55 after about 60 seconds. 1.55 times 10 to the 9th. And here, with the aggressive heuristic settings, we found a solution of 1.4 times 10 to the 9th in about 20 seconds. However, recall that the lower bound before was about 1.1 times 10 to the 9th. Now it's 9 times 10 to the 8th. So by changing the heuristic setting, we've devoted more energy to the finding feasible solutions, to the upper bound, and we've devoted less energy to improving the lower bound. Okay. So the setParam method is designed to be quite flexible. So recall that I typed out the full name of the parameter earlier. You can use wildcards. So HE star is matches all parameters that begin with letters HE. We actually ignore capitalization, so you can type HE star. You type HE star. We just don't care. And if you specify a wildcard and there's not a unique match, we will actually list all the parameters that match. I star. So, if you want to set a parameter that begins with the letter I, here are all your choices. At this point, you may be wondering, how am I going to remember all this? So the Gurobi Interactive Shell includes a fairly extensive help capability. So at the top level, we just have the help command, which gives you a list of the top level Gurobi shell commands. For example, there's the read command, it reads a model from a file. And it also gives you pointers on how to get additional help on any of the Gurobi objects. For example, you can ask for help on a model, and the help on the model lists all the methods that are available on model objects, lists the attributes that are available. I'll talk about attributes more in a second. To the way our help is organized, you can ask for help on the name of the object, or you can also ask for help just using an instance of the object. So remember that M contains a Gurobi model object. If we say help of M, it's the same as saying help of model. And you can also ask for help on methods. So you can say help. You can ask for help on m.optimize, for example. Gives you the name of the routine, the purpose, the arguments, an example of how to use it, and notes. You can also get help on any of the Gurobi parameters. That's available through a command called paramHelp. So recall that we used the heuristics parameter earlier. By saying paramHelp, you can get help on that parameter. Again, this command accepts wildcards, and so you can get help on any parameters that begin with the letters HE. And again, if you just specify a single wildcard that doesn't give you a unique result, it shows you a list of all the matching parameters. So before we continue, actually let me make a few side comments here. So first off, if all you want to do is experiment with parameter settings, read models from files, solve them, maybe save the solution, sorts of things that we've shown in the video so far, you may not actually want to use the interactive shell. We actually have a much lighter interface, the command line interface. So let me just demonstrate that quickly. So the Grobe command line interface is accessed using the command grobecl, and you can specify parameters just using a parameter name equals value syntax. So here we're going to solve model P0033 using setting parameter result file equal to P0033.sol and heuristics equals 0.5. So this is saying when the optimization is done, the result should be written to the file P0033.sol, and the heuristics parameter should be set to value 0.5. So if we just type this in the command line and hit return, so we read model P0033 from a file, we optimized, and we wrote the result to file P0033.sol. So again, if all you want to do is just read a model from a file, solve it, maybe change a few parameters, save the results, grobecl, the command line interface, is a much lighter, much simpler way to do this. So before I talk any more about what you can do with the Gurobi Interactive Shell, Let me talk for a second about what the Gurobi Interactive Shell actually is. So the Gurobi Interactive Shell is just a set of methods and objects that have been added to the Python programming language, to the Python shell. So Python is a very modern scripting language. It includes all the things you'd expect to find in a modern language. It includes functions, classes, objects, modules. It's quite a powerful system. It's also actually quite a popular programming language. The folks who track the popularity of programming languages, a website called Tyobi, lists Python as the 4th most popular programming language right now. So it's quite widely used. So when you start up the Gurobi shell, you probably noticed this before, the first thing you see is Python 2.5.4. So this is a Python message, and that's followed by the Gurobi welcome message. And so when you're in the interactive shell, all we've done is basically just started up Python and printed out our own welcome message. But you are actually in the Python shell right now. And so you can issue Python commands. You can print is a Python command, print 5 times 3. You can define a function, f of x, return x plus 5. So now I can print f of 3, which is 8. You can write loops for I in range 0, 5, print I. So you're sitting inside of a scripting language. So anything you can do from the scripting language, you can do from the Gurobi Interactive Shell. And really all we've done is taken the set of Gurobi methods, the set of Gurobi classes, and just imported them into this Python shell. So when you're learning to use the Gurobi Interactive Shell, you're really learning the Python programming language. So you don't need to know that much about the Python language to use most of the features of the Gurobi Interactive Shell. If you'd like to learn more, there are actually resources available for learning more about Python. Actually, this is quite a nice resource. There's a book called Dive into Python. You can find information at diveintopython.org. It's actually you can get a printed copy, or you can actually just download the book online. So they make it available for download. So again, you don't need to learn much Python to use the Gurobi Interactive Shell, but basically you can learn as much as you want, and the more Python you know, the better you can use the facilities of the Gurobi Interactive Shell. So now I'll return to talking about what you can do with the Gurobi Interactive Shell. I'll be talking about a few more advanced topics now. These are things you can't do with a simple command line tool. First thing I'll talk about is working with multiple models. So recall that in the interactive shell you can read a model from a file. So the read command, which is a command that we have added to the Python shell, takes the name of a file containing a math programming model as input and produces a Gurobi model object as output, and you can assign that model object to a variable. So since this is Python, since this is a programming language, you're not limited to just one variable. So you can read M2. So we can read bel5 into another variable. We can optimize M, which is P0033. We can optimize M2, which is bel5. Another thing we can do is the model objects in Gurobi have a relax method, which takes the mixed integer programming problem and relaxes the integrality constraints. It creates a continuous version. So we can do relax equals m.relax, and what we've done is we've taken M is model P0033 and we've created a continuous version of model P0033. So if I say relax.optimize now, so this is recall that this is the Gurobi dual simplex log. So this is a continuous, relax is a continuous model. So we've just taken the continuous model and optimized that model. So you can read as many models as you like. You can put them into variables, put them into arrays of variables. Basically, it's a programming language. So you can put them. You can do anything you could do in a programming language. Another command I should mention is the models command. This allows you to examine the workspace, if you will, the current set of variables, to see which models are currently loaded. So in the example here, we have model M2, which is model Bell5. We read it from file Bell5. We have model Relax, which is the continuous version of model P0033, and then we have model M, which is the original P0033. So the interactive shell makes it easy for you to work with multiple models. So far we've treated models as black boxes. So we've read models from files, we've optimized them, we've set parameters on them, but we've never really looked inside. To do some of the more advanced things that you can do with the Gurobi Interactive Shell, it's often useful to actually look at what's inside of a Gurobi model object. So let me read model P0033 again. So M is a Gurobi model object. A model actually consists of a set of sub-objects. So within a model we have a set of variable objects. We have a set of constraint objects. We actually have other objects I won't be talking about right now. So let's take a closer look. So the model object has a method on it that allows you to get a list of all the variable objects in the model. So by typing m.getVars, we've gotten a list. The brackets indicate that this is a Python list of variable objects. Each of the items within the less than greater than is an object. It's a Gurobi var object, and this is the name of that variable. So just to show you that these are in fact the variables, if you compute the length of this array, it's 33. So there are 33 variable objects in this model. Similarly, you can get the constraint objects in the model. We've got, should have 16. Yes, we have 16 constraints in the model. Again, this is a list of all the constraints in the model. Things between less than and greater than give you the names of each constraint within the model, each constraint object. So once we have access to the list of variables or constraints in the model, we can use the Python for statement to iterate over the variables or constraints in these lists. So for example, for v in m.getVars, so v is going to iterate over all the variable objects in the model, and then we can do print v.varName. Okay. So what we've done is just iterated through all the variables, and then we've printed for each variable v, we've printed the varName attribute. So variables have attributes, constraints have attributes, models have attributes. I'll talk in more detail about attributes shortly. But in this case, all we've done is loop over the 33 variables and print their names. So let's consider a more complex example. So let's say we want to take the original model, P0033, and we want to set the objective to 0. So rather than trying to optimize an objective function, we just want to find any feasible solution. So we can do this by saying for v in m.getVars. So we're iterating again over all the variables in the model, all the variable objects in the model. And then variable objects have an attribute called obj, which is the linear objective coefficient for that variable. And we can assign a new value to that variable, to that attribute to that variable. So for v in m.getVars, v.obj equals 0. So that has just iterated over all the variables in the model and set the linear objective coefficients to 0. And if we say m.optimize, now we have the same constraints, but we have no objective function, and so when we perform the optimization, what we find is that the heuristic finds a solution. In this case, the objective is 0, because we no longer have an objective function. The objective function is 0. And since the lower bound and upper bound are both 0, at the point at which we find a feasible solution, if the objective is 0, we have the optimal solution, so it terminates there. So that's just a very simple example of how you might modify the model by iterating over the variables or constraints in the model object. Let's now consider a slightly more complicated example. Again, we're going to use model P0033 as our example. I'm reading it from a file again because we've modified the model that's in memory. So we want to get the original objective function back. Recall that the optimal objective for this model is 3089. And let's imagine that we want to know which single variable makes the largest contribution to this objective. So imagine that this objective function represents a cost. Which variable contributes the largest value to this cost? So what we're going to do is we're going to loop over the variables in the model, and for each variable we're going to compute its contribution to the objective, and then we're just going to find the maximum over all variables. And so we're going to have a variable maxObj which captures the maximum value. We're going to loop over all variables in the model, and we're going to compute the objective contribution from this single variable, which is going to be v.x times v.obj. So this is v.x is the x attribute for this variable, which is the value of that variable in the solution, and v.obj is the linear objective term. So we've now computed for variable v the contribution of that variable to the objective, and then if var obj greater than max obj, then max obj equals var obj. And let's keep track of which variable contributed the most as well. Max var equals v. Alright, so we've just iterated over all the variables, and we find max obj is 500. And max var is C175. So what we found, and indeed, if you compute, so max var is the variable that makes the largest contribution. And if you print max var.x, which is the x value for that variable, it's 1.0, and max var.obj is 500. So indeed, variable C175 contributed 500 to the objective, and this was the most expensive variable in the model. So I mentioned that Python is quite a powerful programming language. It's actually got quite a few capabilities for working with lists. So anyone here who's a Python programmer probably looked at the previous example I just showed, the for loop, and said, oh, that's way too much work. I can do that in one line of Python code. And indeed, it's true. So actually, let me show you how you might do this using some of the more sophisticated Python features. I'll actually do it in 2 lines of code instead of one line of code, just to be a bit less opaque. So, the first step would be to use something called list comprehensions in Python. Re and m dot. So what this does is it says build me a list consisting of the values of v.x times v.obj when I iterate over all values in m.getVars. So basically this shows you the objective contribution for each variable in the model. And then the second step is there's a Python function called reduce, which allows you to take an operator and apply it to all members of a list, producing a single result. So it's basically going to take the max over all the members in the in the list. So in this case, we've taken the max over the OBJ's list that we just built, and we get 500. And so you can imagine you could combine this into a single line by just replacing OBJs with what I typed here. So in Python, in a single line, you could find that the maximum objective value contribution for any one variable is 500. So before I continue with further examples of what you can do with the Gurobi Interactive Shell, I want to return to a topic that's come up a couple times. I want to focus some attention on it. It's an important topic, and this is the topic of attributes within the Gurobi interface. Attributes are the primary means of querying and modifying information about the model in Gurobi. So what attributes are available in Gurobi? Let's go back to the help in the interactive shell. You'll notice at the bottom of the help is a topic specifically about Gurobi attributes. So let's get more information on attributes. So if you type help grb.attribute, it gives you a list of all the attributes that are available in the Gurobi interface. There are attributes on the model itself. There are attributes on the variables in the model, attributes on the constraints in the model. There are a variety of different attributes that you can query, and some of them you can also modify. Let's look at model attributes first. So models have a list of attributes. The list is shown here. Model has a number of constraints, number of variables, number of SOS constraints, number of non-zeros, so on and so forth. There's a long list of properties of the model. So let me give you an example of how you would use this. Let's read model P0033 again. And let's look at the number of variables. So if you just type m.numvars, where m is a model object, it gives you the number of variables in that model. Similarly, number of constraints, constraints. So this model has 16 constraints and 33 variables. If we solve the model, there are a number of attributes related to the solution. Sol count gives us the number of solutions that were found in the process of solving the MIP model. So we found the initial heuristic solution, and then we found 2 further solutions, giving a total of 3 solutions found during the solution process. There's m.runtime, which tells you the amount of time that was required for the most recent optimization call. m.objval gives the optimal, or actually the objective value for the current solution to the problem. So there are a variety of attributes that are available. Some of them can be modified and some of them cannot. And the way you modify them is you just assign a new value to the attribute. So an example of an attribute that can't be modified is numvars. So if I try and set numvars to 3, it won't let me. This is you can actually, there are methods for deleting constraints and variables in the model, and so you could delete all but 3 variables, but you can't do it by just setting the attribute. On the other hand, something like the name of the model. The name of the model is initially P0033. We can actually change the name to something else, new. Actually, one thing I should say now is that whenever you make a change to an attribute in the Gurobi interface, we take an approach called a lazy update approach. And so when you make a change to an attribute, it adds the change to a queue of pending changes for that model. And then you clear the queue. You apply the changes in the queue by calling update. So we've made a change to the model name attribute. We call update. And now we query the model name attribute, and the value of that attribute has changed. So these are attributes on the model object. There are also attributes, as I mentioned, on the variables and on the constraints. So for example, variables have lower bounds, upper bounds, objective coefficients, names, they have solution information, so on and so forth. Constraints have senses, right-hand sides, names, solution information. SOS constraints also have attributes. So let me give you an example of that. Here we have. Let me pull out a single variable from this model and get vars 0. So this is choosing variable 0, the first variable in the list of all variables in the model. So recall from earlier examples, I can say v0.x, which gives me the value of this variable in the current solution. I can say v0.varName. The name of this variable is C157. And again, I can make modifications to attributes on variables. So I can say v0.varName equals new, and then I apply the updates. I apply the pending updates to the model, and then if I print v0.varName, the name of that variable is now new. So I've demonstrated how you query and modify attributes on variables. It's very similar for constraints. One more thing I wanted to point out is we actually allow you to store your own data within the Gurobi objects. The only condition is that you have to prefix the name of the item that you want to add to one of our objects with an underscore. And so, for example, you can say v0._x equals my value, and then you can print v0._x. So if you're writing a program and you need to associate your data with variables or constraints in the model, you can do this by just adding it using a name that starts with an underscore. So to summarize, attributes are an important part of the Gurobi interface. They're an important part of the interactive shell, but they're actually also an important part of all of our APIs. This is the means we use for querying and modifying most model information in all of our interfaces. Attributes are fully documented in our reference manual, so if you need additional information on attributes, I suggest that you go consult the reference manual. So now let's return to our overview of the sorts of things you can do with the Gurobi Interactive Shell. So as I've mentioned, the Gurobi Interactive Shell is really just a set of methods and classes that we've added to the Python shell. And just as we've added classes and methods to the Python shell, so you can actually add your own as well. Python is a full-fledged programming language, so any function you can write in Python you can add to your shell. So I'll give a very simple example here, but really the sky's the limit when it comes to customizing the shell. So you'll recall that in the course of this video we've read several files, and several of them have been in the /models directory, for example bel5. So we've got several models stored in this /models directory. So imagine that you have a directory where you normally like to keep the models that you're going to be reading into the interactive shell, and rather than having to type the full path to that directory, you'd like to be able to just give the name of the model and have it read, have the interactive shell read the model directly from that directory. So you can do that by creating your own custom read function. You do this by defining a function in Python. I'll show you how to do that now. Define myRead of name, return read /models/plus name. Alright, so this is the Python syntax for defining a new function. I've defined a new function myRead, which takes one argument, which is a name. And then all this function does is it returns the result of calling read. This is the Gurobi read function, using the argument /models, and then appended, and then your argument to this function is appended to the end of that. So to give an example now, if I try and read model bel5, that fails because bel5 is not in the current directory. However, if I call myRead, then that succeeds. So it's just taken bel5 the function is appended /models to bel5 and return the result of calling the Grobe read function. So if you're likely to want to use this function often, you probably don't want to type it in each time you want to use it. So you can actually save this function to a file and just read it in from that file. So I have saved this in myread.py. So to read this from a function, you actually need to include a bit of Python magic at the beginning of the file. You need to include the statement from Gurobi pi import star. This function basically says that this function is allowed to use methods and classes defined in the Gurobi pi module. In particular, for this particular custom function, we're going to use the Gurobi read method. And in order to import this function into our current environment, we just say from myread import star. And at this point, we have the myread function available from our shell. So you can save this in a file and import it. The Grobe shell actually reads a file every time it starts up, and so another option is you can actually just go and modify the startup file that the Grobe shell reads. So there are details on this in the documentation. So. And I should say that this file that you read, the example I've shown here just has a single custom function, but you can put all of your custom functions in one file and import them all with a single command. So the shell gives you quite a bit of flexibility to customize the set of functions that are available to you. You can basically write whatever functions you like. Now I'll move on to a few more advanced topics. First topic I'll cover is that of adding constraints to an existing model. I'll use example P0033 again. Recall that the optimal solution for this model is 3089. And if you look at the solution, what you find is that 15 binary variables take value 1. Now imagine that you solve this model, you notice that 15 variables take value 1, and you realize that there's a constraint that you didn't include in the problem, you didn't expect it to be violated, that only 14, at most 14 variables can take value 1.0. So what you want to do is you want to modify the model. You want to add an additional constraint limiting the number of binaries that can take value 1.0, and you want to resolve. To do this, we're going to use the add constraint method on the model. Let's ask for help on that method. So the help indicates the syntax for the add constraint call, the purpose, the meanings of the arguments, and it gives you an example. And you can see in the example that an important ingredient in add constraints is going to be a linear expression. So what we're going to do is in our case, we're going to say a linear expression, which is equal to the sum of all the variables in the model, is less than or equal to 14.0. So we're going to build this linear expression using the linexpr constructor. Let me show you how this is going to work in our case. Use a bit of Python magic here. So what I've done is bracket 1.0 times 33. This is just a simple way in Python to create a vector of length 33 where all the elements are the same. All the elements in this case are 1.0. We know that we have 33 variables in our model, and then m.getVars just returns a list of all the variables in the model. And this expression here creates a linear expression object, which is equal the dot product of a vector of all ones with the list of all the variables in the model. And now we can use this to call the add constraint method. So we're going to call m.addConstraint. And we use the linear expression that we just built as the first argument, less equal 14.0. Okay, so that has added the constraint to the model, but recall that we use a lazy update approach, and so this is all it's done is put a request to add the constraint into the queue of changes to the model. We call m.update to clear the queue, to actually apply the update to the model. And then we call m.optimize again. The objective function is still 3089. However, if we look at the solution vector, what we find is in this case we have a solution with 14 variables at 1.0. So it turns out that there are multiple solutions whose objective value is optimal. One of them has 15 variables at 1.0, and the other one, this one, has 14 variables at 1.0. I've just showed you one more advanced example, how to add a constraint to an existing model. Now I'll show you another more advanced example, how to add variables to an existing model. The example I'll use for this is model Stein 10i. It's a model with 15 constraints, 9 variables, and if we optimize the model, what we find is that the model is infeasible. So there's no assignment of values to variables for this model that satisfies the constraints of the model. So if we look at the model, you see it has 9 variables. They're all binary. These are the constraints of the model, and for this particular model, there are no settings of those binary variables that satisfy the constraints. So what we want to do now is ask the question, how much would we have to relax the constraints of the model in order to make the model feasible? In order to do this, what we're going to do is for each constraint in the model, we're going to add a pair of slack variables. One slack allowing the left-hand side of the constraint to go up, another slack allowing the left-hand side to go down, and then we're going to minimize the sum of these slack variables, and that will tell us which constraints need to be relaxed and how much they need to be relaxed in order to make the model feasible. To do this, we're going to use 2 methods. First method we're going to use is the addVar method. This is on a model, so m.add. If we ask for help on m.addVar, this is a method that allows you to add a new variable to an existing model. Here are the arguments it takes. The arguments have default values. One of the arguments is actually a column argument, which allows you to specify the non-zero values in the column corresponding to that new variable. Basically, which rows does that new variable participate in, and what's the coefficient for each row it participates in. So the other method, the other class we're going to use is the column class. Get help on that class. So this is the object that allows you to say for a particular variable which constraints does it participate in and what are the coefficients. So it gives an example here. So this is the constructor for a column object. So it's very similar to the linear expression constructor that we used in the previous example. We have a list of coefficients and a list of constraint objects. And this right here says this particular variable has a 1.0 coefficient in constraint C0 and a 2.0 coefficient in constraint C1. So I'm going to define a function that performs this optimization, this alternate optimization. Call it feasopt. So this function takes a model as its input, and it produces as its output another model where the objective of this other model is to minimize the relaxation of the constraints in order to achieve a feasible solution to the original model. So rather than type this in, I've just entered it into a text editor. I'm showing you the contents of a file here. Again, from Gurobi Pi import star, this is just the Python magic that allows you to use the new function in the interactive shell. And then we define this method feasopt. It takes m, a model, as an argument, as its one argument. First step is it creates a copy of the model. So copy is a method on a model, produces an exact copy of the model. So now f is our copy. This is the thing we're going to modify and the thing we're going to return. First step in this function is to iterate over all the variables in f and set the objective for the existing variables to 0. So we don't care what the original objective is. Our new objective is to minimize the amount of relaxation required on each of the constraints. Our next step is to iterate over all the constraints in f for c and f.getConstraints. And for each constraint in f, we're going to add two variables. We're going to add one variable which allows the left-hand side of the constraint to go down. And the way we do this, so the objective is 1.0, so we're going to be trying to minimize the sum of the relaxations of all the constraints. We're going to specify a column associated with this new variable. Basically, we're saying that this variable has a -1 coefficient in constraint c, which is the current constraint in the iteration. So basically, this is saying that this new variable allows the left-hand side of constraint c to be reduced. And we're also just going to give the new variable a name. We're going to derive the name from the name of the constraint, the current constraint. So we're going to the name of the variable is the name of the constraint with underscore down appended. So this is the slack variable, the artificial variable that we add in order to allow the left-hand side to go down. Similarly, for each constraint, we're going to add a variable that allows the left-hand side to go up arbitrarily. And the difference between this new variable and the other new variable is that in the column constructor, the coefficient is 1.0. And again, we give the variable a name. We're going to use underscore up for these variables. So we iterate over all the constraints, add a variable to allow the constraint to the left-hand side to go up, another to allow the left-hand side to go down. We call f.update. Recall that we use lazy updates, so these modifications to the model don't actually get processed until we call update, and then we return f. So we return the model that has been created by this function. All right, so that function is stored in a file. Recall that we can import, from physopt. File name is physopt.py. Import star. That imports the physopt function into the shell. M equals read stein 10i. F equals physopt of m. So now we have our feasibility version of the original model. We can write this feasibility version to a file, and then we can examine the contents of the file. And you see what we have is, so this portion, basically the first three variables in each constraint, this is the original model. And then in each constraint we've added a artificial variable to allow the left-hand side to go down, artificial to allow the left-hand side to go up, and then the objective function is to minimize the sum of these artificial variables. So now we can optimize this feasibility version of the original model. f.optimize. And what this shows us is the optimal objective for this feasibility model is 1.0. So the total magnitude of the relaxation required to obtain a feasible solution to the original problem is 1.0. And we can print the attribute x, we can print the solution. And what this shows us is that if we reduce the left-hand side of constraint C13 and C14 both by 0.5, the model becomes feasible, and this is the feasible solution. So far we've just been working with existing models, reading models from files, modifying parameters, modifying the models. What I want to show with this last example is that the Gurobi Interactive Shell actually contains the full power of any of the Gurobi interfaces. And in particular, you can use the Gurobi Interactive Shell to build new models and, in fact, build whole applications if you like. So anything you can do with any of the Gurobi interfaces, you can do with the Gurobi Interactive Shell. Of course, I'm not going to build a full application here. I just wanted to show you that it is possible to build a model from scratch. So I'm going to build a very simple model from scratch. The model is going to solve the following problem. So the model will have 10 variables. They'll be binary variables. And the constraint is that among any 3 adjacent variables, only one can take a value 1. And we're going to try to maximize the sum of all the variables in the problem. So we're going to try to find the maximum number of variables that can be set to 1, subject to the constraint that only one among any neighboring 3 can be 1. The first step when you're building a model from scratch is to call the model constructor. So it takes an argument which is the name of the model. So we can call print stats on this model, and indeed what we find is that it's an empty model. It has no constraints, no variables, no non-zeros. Generally, the first thing you do once you have an empty model and want to start building your optimization problem is to add your decision variables. Recall that we are going to be working with 10 decision variables, and they're going to be binary. And our goal is going to be to maximize the sum of these variables. So in other words, they're going to have a linear objective coefficient of 1.0. So let's add 10 variables to this model. So we're going to use a Python loop, and we're going to call the m.addVar. We're going to set the objective to 1.0, and we're going to set the type of the variable to grb.binary. So they're going to be binary variables. Okay, at this point we have added the variables to the model. Because of lazy updates, we need to call update. Now we call print stats again, and indeed what we have now is we have a model still with 0 constraints, but now it has 10 binary variables, and it has non-zero objective coefficients. The objective coefficients are 1.0. Okay, one other thing we need to do here is the objective for this example is maximization. The default objective in Gurobi is minimization. There's a model parameter. There's a model attribute called model sense. By default, it takes a value of 1, which means minimization. You can set it to -1, and that will give us a maximization objective. Next step is to add the constraints in the model. Recall that we need a constraint for each set of 3 contiguous variables, indicating that the sum of the 3 variables has to be less than or equal 1.0. So we'll do that as follows. There are going to be 8 such constraints. We need 8 constraints for 10 variables. We're going to build a linear expression for each constraint. Okay, the linear expression, the coefficients on the linear expression are all 1.0, and the variables, we use m.getVars. This returns a list of all the variables in the model, and then we're interested in a subrange, a subarray from this whole list. This is Python syntax for a subarray. What this says is give me the subarray that begins at index I and goes through index I plus 3, non-inclusive. So this is going to give us a list of 3 contiguous variables whose index starts at I. Then we're going to use that expression to add a constraint to the model. So we're going to say that that expression is less than 1.0. Okay. And then we do an update, and then we can do an m.printstats again. And you see now we have a model that contains 8 constraints and 10 variables. And if we write this model to a file, let's write it to test.lp. We can examine the contents of this file. So you see we have our model. Maximize the sum of the variables subject to sets of 3 contiguous variables less than or equal 1, all the variables binary. We can optimize this model. The optimal solution is 4.0, and if we print the solution, you see that variables 0, 3, 6, and 9 are 1. So it respects the constraint that among three contiguous variables, at most one can take value 1. So we've built a model from scratch here in this example. It's a very simple model, but the point I want to demonstrate here is that there are really no limits on what you can do with the interactive shell. It's the full Gurobi interface. It provides all the capabilities of all the other Gurobi interfaces, and you can use it to build arbitrary models. So this concludes our introduction to the Gurobi Interactive Shell. If you'd like more information, I encourage you to visit our website. On the website you'll find all of our documentation, which includes a quick start guide, gives you a quick overview of the product in general, the reference manual, which gives you the detailed reference information, and a document that gives you an overview of the Gurobi examples. So we include 20 examples in the distribution for each of our programming languages, including the Python interface. So if you want to learn more about the Python interface, you want to see more detailed examples, you can look at the examples on our website. If you sign up for an account on the website, you can also get access to our free trial. So the free trial allows you to install the Gurobi Optimizer to use all of the supported interfaces, and it also allows you to solve models with up to 500 constraints and 500 variables. So the only difference between the free trial and the full commercial product is the limit on the size of the problems you can solve. And if you're an academic, we actually offer full unrestricted licenses, so no constraints at all. We give the full commercial product free to academics. So I encourage you to visit our website for next steps if you want to learn more about Gurobi. Thank you.